Good evening. Tonight's session is on stellar explosions, or as I like to refer to it, things that go bang, but not big bang. We'll get to that shortly after we cover the news. Okay, the folks from Bloomberg Technology were kind enough to take the Blue Origin New Shepard launch with the four, I guess we call them astronauts, folks on board, Bezos and his brother, and Oliver and Wally. They successfully went up, had 90 seconds worth of zero gravity, and then came back down by a parachute, successfully landing not too far from the launch pad. And just to show you that Hubble's back on the air, the Hubble site, the Space Telescope Science Institute, released two pictures. Look, it's still in focus. It still has great resolution. So Hubble is operational. And this was a first. The folks at ALMA, the microwave radio telescope array in the Atacama Desert, South America, they released false color radio image that shows a star. This is in constellation Centaurus. The star is PDS 70. The star is there in the center. But the interesting thing is they also show a planetary formation disk over here. But the most interesting thing is this very difficult to make out little blob right there. The suspect formation of a moon around an exoplanet. This is the first time ALMA's ever imaged such a thing. So that's a first for ALMA. We get to see a planetary protodisk as well as a stellar protodisk, which says that moons around planets and planets around stars kind of all form at the same time. You don't have to wait until the star is done and then the planets are all done and then you get moons. No, it seems to all happen at the same time. By the way, that's an image you would never get visually. It's too small. Radio telescope arrays can observe in tiny fractions of an arc second. So you would never get that level of image. Boeing is going to once again try to launch their Starliner capsule up to the International Space Station. If you follow Boeing, you'll remember that they tried their orbital flight test #1, and it didn't quite go well for the upper stage and could not make it all the way up to the ISS. So it came back down. This is an unmanned craft. This is the step that you have to do before NASA and the FAA will give you the sign off to launch people. So this is their second attempt at an unmanned capsule docking with the International Space Station. In order for the Starliner to dock with the International Space Station, the craft that was currently at that docking port had to relocate to one on the backside. And the one that did that is the SpaceX Crew Dragon that took up 4 astronauts earlier this year to the International Space Station. The second time that's occurred. First time was with 2, second time was with 4. So they had to move it. Now they could probably just use 2 astronauts on board. I don't know if it's an unwritten rule or not, but all 4 astronauts that came up on board this Crew Dragon flight got in the Crew Dragon to undock it, move it around, and then redock it on the other port. Russia was making noise like they were going to back out of the International Space Station and maybe do their own thing. Well, on July 21st, we have evidence to the contrary. Since about 2007, Russia has been wanting to put a larger crew quarters module up in space and attach it to the International Space Station, where there's right now a Russian docking port. So that's what they did. They launched a new module to the International Space Station called Nauka, which I believe is just Russian for science. It has a docking port. It connects on to where the current docking port is. And it has crew quarters. It has accommodations for Russian astronauts. So they're actually going to be docking that soon. It had some foibles on the way up. They had some engine problems and couldn't get it to open up everything it needed to be opened up. But apparently they've resolved that and it's on its way to the ISS. The port that's there now will actually be directed to burn up. So they'll disconnect that one and send it down to burn up, and they'll connect the new one up to where the old one came from. So for a while, they'll have to close off that section of the ISS. Otherwise, it all leaks to space. So it'll take them, I don't know, probably a month or two to get all that up and working in the parking maneuver. But it's nice to see that Russia's still adding modules to the ISS. The United Launch Alliance lost that contract to SpaceX, and they're going to launch it on a Falcon Heavy. Not only that, but apparently SpaceX reduced the price somewhat. So NASA got a bargain, which is good for our tax dollars, and they're going to be using a launch vehicle that's already flown before. There's this site called Primal Space on YouTube, and they occasionally produce some fairly interesting videos. I had mentioned before when a Falcon rocket lands on one of the drone ships offshore, that right as the rocket is landing, you lose the video, and it's due to the plasma from the rocket engines. And then once the rocket engine shuts off, you can see the rocket sitting there happily on the drone ship. And SpaceX said, no, we need to find a solution to this problem. And it involves Starlink. And this video, which is under 10 minutes in length, explains all the nuances that they had to go through so that this last SpaceX drone ship landing, you got to see it all the way until it landed on the drone ship, which was a first. When people don't think that SpaceX pays attention to detail, this video is kind of counterintuitive. And also a couple of weeks ago on the commercial US spaceports presentation, I mentioned that SpaceX was buying used oil rigs, floating oil rigs, to use as launch and landing platforms. And this Primal Space video goes into some detail as to what they're going to have to do to get these former oil rigs to the point where they can be usable by SpaceX to launch and land rockets. The one thing I hadn't counted on was if you look at the Falcon 9 launches that occur today, just a few seconds before launch, you see an enormous amount of water pumped onto the launch platform, not to just cool it down, but also for sound shockwave suppression. And when you start talking about Falcon Heavy and the Starship launches, the decibel level of the acoustic force is enough to shatter windows. So they're going to do this out at sea, where they can direct the exhaust nozzle into the Gulf of Mexico or the Atlantic Ocean to solve that problem, rather than pumping lots of water on it. So for a number of years, we've thought that Mars had a cold, hard core, like its core had solidified, and that's the reason why it has such a low amplitude magnetic field, and that's why it doesn't have obvious auroras, and that's why there's so much solar radiation on the surface of Mars, and well, that kind of all went by the wayside when it's been determined after many years of Marsquake detection and recording by the NASA InSight landers seismograph that Mars has a liquid core. Liquid meaning molten rock. So it's still got a hot enough core to have it molten. That means there ought to be a stronger magnetic field if the core is not molten rock, but has some metal to it, has some molten nickel in it. Much like the Earth has a nickel iron molten core. So they're going to have to go back and do some explaining as to why what. because not only have they determined that Mars has a molten core, but in another session that we'll get to in a couple of weeks, Mars actually has aurora, just like the Earth has aurora. The difference is the auroras on Mars appear in ultraviolet. So if we were looking at them in our color photos, we wouldn't see them. But when you have craft that are orbiting Mars that can take pictures in ultraviolet, all of a sudden you can see auroras and, explain how those occur. And while we're talking about Mars, the NASA Perseverance Mars rover is about to acquire its first samples of soil, which is going to be, dirt, small pebbles, maybe some larger pebbles, not, fist-sized rocks or anything, but some obvious samples. So when they find something interesting, they can send the rover over on top of it, and the arm comes out, scoops up a sample, puts it inside of a sealed sample container. And when the rack of samples gets full, they can actually drop off the rack of samples, and a later craft that lands on Mars and is a rover will have a specific mission to go find the sample containers, pick them up, bring them back to its base platform, and then launch those back to Earth. So think of it as it's a very long-term, forward-looking sampling capability. But Perseverance is the first one that's going to go out there and grab up some samples and sort of drop them off for later pickup. So the Event Horizon Telescope has some artificial intelligence in its image analysis. That's how it could recognize what does a black hole look like from all the other pictures it was taking. And NASA is now pursuing that for its own imagery for other than things like black holes. So the first thing that they're going to be using this on is the SDO, the Solar Dynamics Observatory, to better analyze images of the sun. But they're also going to be doing it for other things. So if you wanted to take some of the images that NASA's already taken and create a 3D model of something like the asteroid Eros, you can do that. There'll be software for doing that. So look for new fly-throughs, new 3D models, and maybe some new 3D printable models. Because if you remember, I printed Bennu. And also on the Event Horizon Telescope, they've taken another picture of a black hole, or the accretion disk of a black hole. This time it's Centaurus A. It's a what they call a radio galaxy. It's not bright enough in radio to be called a quasar or a blazar. It's just a radio galaxy. And they took a picture, and this time they actually got the relativistic jets out the top and bottom of it. But if you're looking at it optically, you'll see this kind of stuff. If you're looking at it in other forms of energy, you'll see this. But if you zoom up close enough in radio, you actually see just some red streaks. But it's very good at the resolution for what they took the picture of in radio using this Earth-sized radio telescope array. The fact that they can actually image something that far away, and the length of the segment that they took a picture of the jets is how far light travels in one Earth day. So it's a very short segment. But that's with the Event Horizon Telescope. If you remember from years ago, we did a demonstration at the Broward Library Creation Station using the Microsoft HoloLens 3D viewer. And what Microsoft did was create a display that also had a camera on it, so they could overlay your live view of a scene with graphics. So if, let's say, you're an aircraft mechanic looking at a jet engine part, while you're looking at the part, it could present on the display in your heads up, the parts list and which part you're pointing at and things like that. So that was Microsoft's approach. Whereas Oculus, I think they're owned by Facebook, Oculus wanted to get into 3D virtual environments where they show you something, they obscure your outside worldview, and they show you something that allows you to be in a scene that might not exist in reality. You're walking around on Mars, put you in a virtual environment, a virtual reality environment. But in order to do this, the software they came up with for creating interoperability between the headset and all its components, the video, the audio, the head positioning, to get all that to work together, they came up with a proprietary software interface for it. And now, because there's an open consortium-based version called OpenXR, Oculus has decided to, it says killing off, but they're actually going to be doing something called deprecating, which means as of a near-term date, they'll say, nobody do anything new using our old proprietary stuff. Now use the OpenXR interface that other people can create equipment for and write software for. So it opens things up. And a couple of years down the road, they'll say, we no longer support our proprietary, but we will support OpenXR. So look for that migration. The folks that do the Steam virtual headset stuff have already moved to OpenXR. I think it was last year. But on the same front, Oculus came with what they call a pass-through software interface that allows you to do things like the Microsoft HoloLens, but using the Oculus headset. Okay, you're going to need a camera first that lets you see what the outside world is looking at. And this picture they're showing you on the Verge website here is missing the camera. So you would see a camera on the front of the Oculus headset. So you would have the ability to overlay, what the outside world looks like with what the VR environment looks like. And what she's holding is the VR hand control. The real crux of it is they got to make all this stuff smaller, cheaper, and faster before it's ever going to catch on. So last week I mentioned that NHTSA, the U.S. Highway Transportation Safety Administration, said, you remember those Chevy Bolts that you had a problem with, you did a recall on because they were catching fire? Even after you did the retrofit, we've got 2 of them that still caught fire. So Chevy did a second recall on Bolts dated 2017 to 2019, and they're going to attempt to once again resolve the battery heating up, causing the seats to catch fire, causing the vehicle to catch fire. They're going to attempt to come up with a resolution, but they've also added some instructions for use in medical devices. Whenever somebody's just using something improperly, they change the instructions for use because it's sometimes not worth it to redesign everything to make it a lot more cumbersome to eliminate a potential that's very low. It's a form of risk management. So what GM Chevrolet did is say, and if you've got a 2017 to 2019 Bolt, even after you've done this retrofit, we suggest if you're charging it up, don't charge it up beyond 90%. And if you're discharging it, don't discharge it more than down to 10%. And after you've recently charged it up, don't park it near buildings or things like shrubbery and trees and bushes and stuff that might catch fire, just in case. So they're going to be doing a second retrofit and added some just in case instructions. Okay, now this I found very entertaining. Down in Australia, they have trash bins, or dumpsters as they call them, that are similar to our, the trash can you take out front for the garbage people to pick up your trash. And parrots in Australia have learned how, the bigger parrots, these are not small. I don't think they have a picture here, do they? They're cockatoos, sulfur-crested cockatoo. They've learned how to dumpster dive. Apparently, they watched people after you take your trash can out, if you have something extra to throw away, you think nothing of walking out to the trash can, lifting the lid, throwing the extra trash in, and then closing the lid. Apparently, the parrots have watched this. The parrots, now these are wild parrots in Australia. They've realized that they can do that. So they use their beak to lift the lid, and then they walk around the rim of the trash can, opening the lid until the lid flips over backwards. And now they can fly into the trash can and get out all those good veggies that humans have disposed of. That was interesting, but apparently a lot of parrots are all of a sudden doing this. And they monitored it. They had people watching it, nature and folks watching this. And what they found out was when a parrot learns how to do this, other parrots will watch the parrot and then mimic that behavior on their own. So they're actually learning by watching how to do this on their own. So whenever you think of parrots as, those are rather smart birds, or you watch a cockatoo try to mimic human speech, oh, they're rather clever. Or you can watch crows learning to use tools to ferret things out by, taking little branches off and then taking stems off of those and using it as a tool to grab and poke things. Parrots are now dumpster diving in Australia. I wonder how soon that will catch on. Will it be limited to just Australia, or will the parrots in New Zealand and other places suddenly learn how to dumpster dive? So, as I say, put a push pin in that and take a look at it later. Posted the Data is Electrons presentation from last week on the YouTube page. So if you missed last week, you can take a look at that. And I don't know how many of you followed up on the link that I provided for the scheduling of it, but Jill Tarter, formerly of SETI, she's now SETI Emeritus. I think she still does some promotion for SETI. Did a presentation. It was for the public. There was a follow-up session that was private for members of Astronomical Society of the Pacific that paid to be at the session, the online sessions that they were holding. So Jill took some questions, and there's some guy named Broward Astronomy that posted a question on the chat saying, do you think SETI should add gravitational wave detection to their search for extraterrestrial intelligence? And she said, yes, but they don't have the money or the space for it, thinking that in order to do gravitational wave detection, you needed detectors the size of LIGO. So I sent a follow-up message to the ASP person that was the host of the session saying, you might want to pass on to Jill that the detectors have started using microwaves in spherical chambers, and now they're very much smaller. They're meter size instead of the size of LIGO. So we'll see if SETI suddenly has a branch out like they did with lasers. They started out as radio astronomy, and then they went into laser optical looking for ET. And let's see if they suddenly sprout a new branch of gravitational wave modulation using these smaller detectors. One more thing I'll mention, if you read it in the email, I've been having this common recurring question of, when am I going to go public with these sessions so that anybody can join, anybody can be a member? And I found a path for doing that. Some of the Zoom sessions that I watch, the Zoom session requires login, membership, account, those kinds of things. But then they split it out to Facebook Live. And for the general public that are not members, they let them watch, listen, chat, text chat into the session. That way you have a partitioned off area for the more interactive folks, that is the Zoom session. And then you have the more publicly open where people can watch and comment, which is the Facebook Live session. I'm not going to be transitioning our sessions to Facebook Live, but I might split off a spur. So while we're doing our live thing with interacting members, the general public can, partake of the session from a listening, watching, and chatting. The problem is I'm going to have another thing I have to pay attention to. But I also realized I was reading over Patreon's capabilities, and I originally thought that Patreon was okay. So somebody wants to donate $5, they can donate $5. No. Sorry. Patreon is a recurring benefactor thing. When you see these YouTube things and somebody, does does $5 on Patreon, that's they signed up for $5 a month automatic withdrawal. And I think $5 is the minimum they can do. Okay, that's a $60 donation. Now we're talking about, serious annual money. But the way that they're offsetting that is the YouTuber will have merchandise that is branded, interesting, whatever, be it mugs or t-shirts or whatever they choose to offer, and that the Patreon benefactors will receive a discount on the merchandise to offset their donation. So I'm going to take a look at that to see, if it makes sense. But initially, it will just be for those that are the general public, the sort of great unwashed public that just wants to snoop in and see what's going on. I'll do a split out to Facebook Live for these live sessions. They can already watch the edited sessions publicly on YouTube, but the live sessions, as you know, have more interactions and some of its personal interactions, and I usually edit those out of the publicly posted, but that won't be the case if we break out a Facebook Live. So I will have to let people be advised of what's going on and when you have other people that are listening. So that being said, where's the presentation? Oh, also in the email I sent around, it included a list of the upcoming presentations. So if people are going, and what are you going to do next week? Well, what about the week after that, and the week after that, and week after that? So I think I put out like 5 different things that are in the queue that I'm working on. And the one farthest out is the James Webb Space Telescope presentation to be given the week after they successfully launch it.
Is there a launch date for that thing?
Happy Halloween. It's October 31st.
Oh.
That's when they plan on launching it. Now, the folks down in South America say it may not actually be that date. It may be a week or so later into November, because they're having issues at the launch complex having nothing to do with the Webb telescope. Now, the Webb telescope is in California. How's it going to get down to South America?
By boat.
By boat. When is it going to be going down to South America? That's top secret. They don't want any pirates hijacking the ocean-going James Webb Space Telescope and holding it for ransom. But if you're looking at a $1 billion telescope, so you sit offshore of the cargo shipyard where they're going to be launching it from, because that's the closest one to NASA JPL's facility. So you just wait. You're on, stakeout. And when you see the big white boxes being loaded on board the ship and down into the cargo hold, there goes the Webb. And then when the ship goes out to sea, you wait until it gets into open ocean waters. So, I could say, nice try, JPL, trying to.
Yeah, maybe they'll have an escort,
I think the US Navy should escort it.
Yeah, sure.
Yeah. Because, if people look closely, NASA is actually a division of the US Department of Defense, for people that didn't know that.
But it doesn't have to be ostentatious. They could escort it with submarines or something.
No, I think it has to be ostentatious. You don't want anybody even trying it. So I don't think it needs an aircraft carrier flotilla, but I would think some of the most high-tech, modern-looking missile cruisers. You know, the ones that look like they're stealthy with all the flat panels on them. The one that's like up on a hydrofoil-looking fins.
Yeah.
Put a couple of those out there alongside the ship. Nobody's going to think twice about it.
Yeah, well, the pirates are in rowboats, you know.
Yeah, but these things have lasers, Gatling guns, and missiles.
Yeah.
They'll take out your rowboat quickly. And then, of course, having a deployment of Marines on board the ship, standing at the stanchions, M16s in hand. So if you think you're going to sneak up on your rowboat, climb up their rope that they throw up there, you got somebody waiting for you at the top. I think there's a way to deal with this. So welcome. Tonight's discussion is going to be on stellar explosions, or things that go bang but not big bang. There's been a lot of science programs, educational presentations on all the different ways that stars can produce explosions. And then after the explosion, what happens? What's the, what do the shock waves do? What's the residue? What's the remnant of the explosion? Are they one-time events? Do they happen more than once? Are they recurring? So that's what we're going to cover tonight is stellar explosions, their effects, and what's left over afterward. Okay, we've thought as a human species, we've had a good beat on things a number of times. And what we're now learning about when stars go boom is new science, because we're getting finer detail on what happened before, what happened, and what was left afterwards. So if you think back to ancient Greece, they wanted to try and execute a particular Greek citizen for believing that the sun and moon were not gods. He thought it was a burning rock. It kind of looked like, if you heat up a stone in the fire and it glows red, that must be what the sun is. But then they said, nah, what's heating it up? What's the source of the heat? And it has to last forever. So Aristotle, some people might be aware of his existence, said, no, the sun is made of eternal ether, and therefore it needs no fuel source and will last forever. Second time they got it wrong. In the 1600s, we came up with this lovely thing called scientific method that we thought would get rid of such things. But apparently, even after the scientific method came out, once somebody said, well, we arrived at this through the scientific method, therefore it's scientific fact. And they ignored the fact that it needs to continue. You need to look for newer observations that might change sort of well-founded science. Nope. Scientists became dogmatic in their pretenses about this is the science and we've proven it and it's never going to change. So in 1667, not too soon after scientific method was a thing that people were using, Johann Beecher came up and said, I've got an explanation of what combustion is all about. So when you burn something that came from the earth, from terra pinguis, this is what combustion is all about. And a student of his reworked it in 1697 and came up with this newfound material called phlogiston. And phlogiston was the stuff that makes things burn. And when you run out of phlogiston, it doesn't burn anymore. So if you take a log and you set it on fire, you're allowing the phlogiston to escape. And once all the phlogistons escape, it's now a charred item and it no longer burns. Made sense at the time. And It was still in chemistry texts as late as 1723 that combustion was all about phlogiston. And at one time they thought that the element hydrogen was actually a pure form of phlogiston. And if you think I'm making this up, you can visit the wiki page on phlogiston theory. So a guy named Lavoisier, the microscope guy, in 1772 said, I don't think that's right because, and he came up with a laundry list of exceptional conditions to the phlogiston theory and said, you guys have just got it wrong, and here's the new way to think about it. So, okay. But it wasn't until the 1800s that it was well received enough as the explanation for combustion that people stopped referring to phlogiston. I guess maybe it was because they just love the funny word. It's actually a Greek word. In 1854, a guy named Helmholtz, the same guy that came up with the conservation of momentum in physics, knew the sun couldn't be fueled by something combustible like phlogiston or wood or coal, because you could never have a big enough pile of it to last for as many years, as many millions of years at the time, millions, not billions, as many millions of years as they believed the sun existed. So he came up with a different scientific method approved approach called gravitational contraction. They knew from observations that stars change in brightness. Yeah, there are stars out there that have variable brightness. The brightness changes over time, and they refer to that as gravitational contraction. And it's these squeezings that keep stars fueled. So the sun will never burn out because it has gravitational contraction. And if you want to look up the Helmholtz mechanism, there's a link to it. So it wasn't until 1939, a guy named Hans Bethe, who posthumously received his Nobel Prize in 1967, great going that, decided that maybe it was nuclear fission. No, nuclear fusion, because fission runs out too. So when we were playing with reactors, we said, maybe it's something like that. And then when they came up with well, there's something that produces more energy than fission, and it's fusion. Okay, maybe that's how stars work. But they didn't believe Bethe, and they actually believed that it was Fred Hoyle, the guy of Big Bang theory, the guy who came up with Big Bang as a phrase to say, it can't possibly exist. That's just a Big Bang. And, the universe is a steady state. It's always been here. It's always going to be here. That was Hoyle's approach, steady state. So he put that forth in 1946 that maybe stars go bang. But they posthumously awarded the actual discovery to Bethe in 67. So it made me wonder why, when the fuel source of stars is exhausted, they don't refer to the star as being phlogisticated, which was actually the term they use for when you take that piece of wood and it runs out of phlogiston, it's phlogisticated. So why wouldn't stars be phlogisticated when they become white dwarfs? It would keep the fun word around, but apparently not. They're white dwarfs. So there's a presentation by Whoopi Goldberg, a video that we used to show called Lives of Stars. Wasn't all that great a presentation, but it did go through the lives of stars. Stars are fusion reaction systems that produce materials, produce elements from light elements. They fuse them to make heavier and heavier elements. It's a thing called nucleosynthesis. So they start out with hydrogen, maybe a little helium, and then as they compress, they turn on the fusion, and the fusion makes heavier elements, the ash of fusion. So we start out with hydrogen, we get helium, then lithium, carbon, neon, oxygen, silicon. So while stars are burning, they're producing these elements until they can no longer fuse the next element up in the list and have it produce even more energy. See, as you go from helium to lithium to carbon, you're going up to higher and higher levels of energy as a result of the fusion, and therefore you can sustain the outward pressure against the gravitational field that's trying to collapse the star. But as soon as you get to iron, you're not going to fuse iron and produce more energy than it takes to fuse the iron. Therefore, gravity wins and the star collapses in on itself. That was what they thought was a supernova. And now they're finding out that no, the bangs they were watching, the bangs they were observing and recording actually came from several things. It's, you know, they go bang, but how big a bang? What was before the bang? What kind of residue after the bang? And now they're coming out with all these new approaches to when stars go boom, what happens? So the first one they came up with is binary star systems. And you may have actually seen the Science Channel program to discuss supernovas and how supernovas are really this pairing of stars, not just one star running out of fuel, but the more dominant ones are pairing of stars. And how when one runs out and it goes boom, it can take the other one with it. And when it does that, the other one comes back and reclaims itself. But they now have all these new categories. They have novas and supernovas and hypernovas and false supernovas or unnovas. And then when the nova is done, what kind of things are left over? It could be nebular clouds, white dwarfs, neutron stars, magnetars, or the ever popular black hole. So why stars go boom? It's essentially about size, temperature, and spin rate, and then crossing a threshold, a limit. So when you add too much material to a star, this is sort of when the white dwarf sucks material off of the red giant next to it, and eventually it just accumulates so much of it around the outside of the white dwarf that it goes into fusion. It reaches the thermal limit, you get fusion, and it goes boom. It basically tries to turn on a star on the outside of a star. When it runs low on fuel, it can collapse, might rebound, but it goes boom. So that's the classical supernova. And then when stars cross certain defined thresholds, the limits, you may see this as Chandrasekhar limits. So when you see things like it's a stellar mass black hole, or how big is that neutron star? And there's small, medium, and large, and nothing in between. First they had small and large and nothing in between, and now they've got medium-sized ones. So science changed, and now there's something in between. So look for more observations to give us new science. So here's the classical nova. It's a pair instability nova. You have a white dwarf, and next to it, you have a red giant. And the high gravity of the white dwarf sucks material off the red giant, and it accumulates, forming an accretion disk around the white dwarf. And when it builds up to a certain level, it starts to use gravity to compress that stellar material. So it kind of ignites a star on the outside of the white dwarf. So a star turning on the outside of a white dwarf is a very energetic thing, and it shreds maybe both stars, maybe just the red giant, but it leaves this core left. And the core that's left starts sucking in via gravity and collecting the material that's left over. So when they're recurring, it means that, well, it didn't completely blow away the red giant, and the white dwarf wasn't blown away completely. It just blew all this accreted material out, and then it sucks it back in again, and the white dwarf does its old trick of sucking material off the red giant, and it happens again. This is a recurring instability nova. So how it occurs, we got a good handle on that. When it's going to occur, we kind of know the thresholds, one of those Chandrasekars. We kind of know, but what possible sizes are there and how often can it occur? And can we set a stopwatch to when it's going to occur? Those are all up in the air. We need more observations. Okay, this is the laundry list. People have heard that was a supernova, but what kind of supernova? And you basically have three classes of supernova. If as a result of the supernova, all the hydrogen goes away, so it completely, in the explosion, it completely exhausts all the hydrogen, makes heavier elements, that's called a type 1. And it uses the Roman numeral 1, but since that kind of looks like an I put in parentheses type 1. And then below that, you have classifications of what's left afterwards and whether there's any helium in it, whether it consumed all the helium. So you've got a type 1A, a type 1B, and a type 1C. Well, what if it didn't completely destroy all the hydrogen? That's a type 2, where the hydrogen isn't fully exhausted. And then you start looking at the spectroscopic lines, what kind of elements are left? What is its brightness? Did it get bright and then stop? Or did it get bright and then start getting dim again? And where did it plateau? How dim did it get to before it stopped getting dim? Or did it, go into a black hole where it gets really dim? So you have various types of type 2, and then you have subtypes of type 2. And then they said, well, we've got some that don't quite fit. So rather than calling them type other, they used up the other numbers. So you've got type 3, type 4, and type 5. These are not additional types. These are subtypes of the ones they already have. So it's gotten, they put up enough fine grain on these that it's starting to get confusing and the numbering scheme is no longer uniform. But all these are considered supernovas. So a type 1A is one where you have a core collapse supernova. The hydrogen is fully exhausted. This is the classical one where you reach iron and a core collapse bounces and you get a supernova. An example of this is the type 1A supernova from 2014 in the galaxy M82. Here's a type 2 supernova. We've got a couple of those. They're harder to detect because you have to examine them afterwards. So whatever the star was before, not as important, but what the spectra is of the star after the explosion, whether or not it has any hydrogen remaining. If it's a type 1A, no hydrogen remains. If it's a type 2, it's kind of like a 1A, but we found some hydrogen afterwards. So the 1987A supernova in the Large Magellanic Cloud is a type 2. Now, could they figure that out initially? No, because you have to wait until the brightness of the nova dies down until you can see what light is left. Whereas when it stabilizes, and now you can start to do the spectral analysis and find out, hey, looky, there's some hydrogen left. Well, they found stars that are not in a nova state that did undergo nova, and they were reported by the Kepler spacecraft. So they just called them the observation 2011A and 2011B. These were incomplete type 1A supernovas that happened a long time ago. And because Kepler was looking at these stars in, I think they were in Cygnus because they're 2011. That's just what they saw. Type 5. Notice I've skipped the type 3 and type 4 and things like that because remember, they're just offshoots of others. A type 5 fails to destroy the original star. So you can have a type 1A and the original star didn't go away. It didn't become a neutron star or a white dwarf or even a black hole. Hey, there's still a star there. But it did use up all of its hydrogen. That's why it's a 1A. But when they look at it afterwards, after it's dimmed back down, and realize, wait a minute, there's still a star here. That's a type 5. So in 1977 through 1992, they made observations of a star and the galaxy NGC 1313, and the supernova remnant said, hey, there's still a star here. We were denied the complete destruction of this star by the supernova, so type 5. Okay, if you've watched the Science Channel program, you've probably heard of, oh no, it's a hypernova. What's a hypernova? So if you have a star that is spinning rapidly, and it's a massive blue-white star, and it collapses directly into a black hole, it's going to result in a long-duration gamma ray burst. But gamma ray burst is supposed to be fast. No, that's a fast burst. This is a long-duration gamma burst. It'll be 100 times brighter, nice round number, 100, not 98, not 102, but 100, which means it's in the ballpark. It's about 100 times brighter than a type 1b, but it has the spectral lines of a type 1c. So it has additional elements in it. But it's because it was spinning so fast that it kind of held itself in. So when it did go supernova, it actually went bang, much greater, 100 times brighter than it would have had it not been spinning so fast. And supernova 2016 APS is an example of that. And the latest one, so hypernova wasn't big enough. So now we have a magnetorotational hypernova. So just spinning doesn't hold itself in tight enough. You need a magnetic field on the outside of the spin that holds itself in even longer. This is like a girdle around the star, a magnetic girdle around the star that even though it wants to explode, I'm sorry, you're going to have to build up even more explosive force. So it's not 100 times, it's 10 times the 100 times. So you now have like 1,000 times of a normal nova, and it's a magnetorotational hypernova. So they have one candidate for this so far. These are big. Obviously, there's a lot of things that have to happen in order for this to occur. The original star was about 25 times the mass of the sun. So it may have been a blue-white, but it wasn't that big a star. But ultimately, it will fall into being a black hole. But since it's compressing so much tighter, it can actually fuse heavier elements. So if you're looking for silver or uranium, they're now postulating that this is where that comes from, because their other analysis of the heavier elements that come out of supernovas couldn't quite get together and come up with silver and uranium. The simulations didn't work out. But when you come up with the magnetorotational hypernova, hey, look, we now have silver and uranium coming out of the heavier element fusions. Okay, this is my favorite one. This is one where a star, usually a red giant, enters its supernova phase, and rather than detonating, it just goes poof and collapses straight into a black hole. So you have a red supergiant that one day is a giant red star, kind of like a Betelgeuse in Orion. And then one day it's just not visible anymore. It becomes a stellar mass black hole. So until it forms its accretion disk around the black hole, there's nothing to look at. All the light just goes away into this tiny little dot. So originally they called them unnovas, but that wasn't apparently a professional enough term. So now they call them failed supernovas. And they actually have a candidate, AT 2018 COW. We've got to have the funny acronyms. It's a cow star. I'm sure they have a good explanation of collapsed object without nova or something. I don't know. But AT 2018 cow is a potential failed supernova, a red supergiant that just went poof and became a black hole. So that's the things that go collapse, poofed. What's the end product? So after this happens, what's the residue? What do we have left? If it's not an energetic enough explosion, the star just literally just spills its guts, and you have nebular clouds, which can, once again have hydrogen and helium left over, but some carbon, some organic, methane, some organic compounds. So you go from a star, a star that came out of the nebular clouds of a stellar nursery, ignited, and after some period of time, maybe millions of years, blows its guts out. And once again, you're back to a nebular cloud to, millions of years later, collapse in and ignite again. So you can have a cycle. As long as it never gets big enough to go through a big enough energetic result, you can have a cycle. When the shock wave comes out of a nova, it can actually compress other nebular clouds to create new stars. So an end product of a star going nova can be new stars because of the shock wave compression of the nebular material produced by the star. So a next step up is there's nothing else in the area. It blows its guts out a very long distance, so it's not going to collapse back in anytime soon. So you have this lone white dwarf or a zombie star that is not going to be sucking material off of a nearby red supergiant. So it's just a white dwarf. This is the ultimate fate of our sun. Is we'll go through a expansion period, and then it will collapse down and become a white dwarf. If you get a collapse down far enough where you actually squeeze atoms and you strip the atoms of their individual particle characteristics down to neutrons, you're basically converting all the electrons into neutrons, you get a neutron star. And a rotating neutron star whose radio beam is facing us is a pulsar. If you collapse that neutron star down even tighter, where it has an enormous magnetic field that makes the energy coming out even greater, and it might spin faster and be tighter compressed, that's called a magnetar. It's basically a magnetic neutron star. These are compressed so tightly that a mountain range on a magnetar might only be a couple of millimeters in height. And should there ever be a shift of a fraction of a millimeter, that might actually be a source for a fast radio burst or a gravitational wave. Postulation by astrophysicists as to where all those gravitational waves and fast radio bursts are coming from. It may be a neutron star undergoing a stellar quake. And of course, if you take it to the extreme, it collapses down so far and nothing's coming out, and now you have a black hole. So what about the explosion itself? As I've mentioned, you can have explosions that have varying levels of intensity and varying amounts of material coming out of them. So if you want heavier elements, you're going to need a bigger shock wave, and it's going to have more guts coming out for it to compress to make heavier elements. So the shock wave coming out can get in the way of itself. The best way to describe this is if you were thinking of a star as an onion, the inner layers wanting to explode outward will first have to encounter the outer layers. And if the outer layers can't rip open or get out of the way fast enough, you'll actually have enough force that the outer layer elements that are already higher elements than helium and hydrogen, it might be carbon, they get fused under compression even more so as the shock wave wants to get out of the star. And that's where you get the next heavier elements. You get selenium, which is number 34, mercury, 80, and silver, platinum, and gold. So this is referred to as the P process. Couldn't come up with something more exotic than P process. Yes, there are other letters, so we'll get to those. So you get your next heavier elements by the shock wave compressing the outer layers of the star on the way to blowing it up. Now, this additional fusion obviously takes place in small fractions of a second, because the explosive force is not just going to go, well, I'd really like to explode, but you're just not getting out of the way fast enough. No, it's going to be small fractions of a second that all this happens and produces the abundant heavier materials here. And then the shock wave itself. So the shock wave, once it's gotten out of the star, out of the body of the star itself, is still compressing things on the way out. So the shock wave actually starts to lose energy on the outer edge of the shock wave, and the inner, still energetic part of the shock wave is going to be pressing on that. And that's where you get the next up fusion. This is kind of the mid-range stuff. Your sulfur, argon, calcium, titanium, chromium, some iron, nickel, and zirconium. You can tell these are the heavier things that take a whole lot of energy to fuse to make these elements. We went from the P process, we're now in the S process. There's a pattern happening here. So this is the original concept of nucleosynthesis. But there were some elements left out. Where does the heavier radioactive materials, the should be longer lived, but very radioactive stuff like uranium, thorium, californium, einsteinium, and fermium. Where are these coming from? If you have neutron stars that are orbiting one another and they fall in and you get the neutron star to neutron star merger, which is a huge amount of force, that's where you get additional nucleosynthesis known as the R process. And it's postulated that the explosion of maybe magnetorotational hypernovas or merging neutron stars is how you get to that next level up, levels of force to create these higher order radioactive materials. So that's our process. So if you remember this, we had this vinyl poster at the observatory that we would show as the life of stars. It took me a while to find this. There was a lot of variations of it to get out of the way of the original producer of the poster, but I actually picked this image up off of the NASA website where they talk about stellar evolution. So they were the ones that commissioned this poster to be created. So getting it from them shouldn't be any copyrighted issue. So it's now overly simplistic. There are other kinds of novas that aren't pictured here. There are recurring novas that aren't pictured here. So this is overly simplistic. We need a new picture. I don't have a new picture. I'm not the artistic type enough to come up with these kinds of things, but I did come up with a diagram. So if we wanted to make a graphic, if somebody like Helen or somebody wanted to make a pretty picture out of it, here's the new process. At the formation of our universe, you had subatomic particles, quarks and gluons, that condensed down into the initial hydrogen, helium, the progenitors of carbon and some organics and maybe some of the heavier stuff. That collapsed down into the earliest stars, and then they produced the next generation stars. And ultimately, you had these nebular clouds that produced the next generation of stars. And then when those things ran out of their fuel, then you now have more kinds of explosions. And then you have your dwarf stars, neutron stars, magnetars, and black holes. And then the, R, S, and P processes that describe what this explosion does and how it creates things. And then you have the nebular cloud result that loops you back around to the simple gas and dust progenitor organics making new stars. And until it makes everything into heavier elements, you're going to have this cycle going around. It may take millions to maybe billions of years for some of these cycles to take place, but so long as nothing stops them, they're going to go through these cycles until there's nothing left but heavier elements that will no longer fuse.
May I ask a question?
Sure.
Okay. Isn't the circle the same up until when you get to the explosion and then you have all the new things, or is there something else new in the previous section that I don't see?
No. If you look on the left side of this diagram,
Okay.
that's when you first got the Big Bang and you had quarks and gluons. These
Right.
were the precursors to them condensing into simple things like hydrogen, helium, mostly hydrogen. And then when that sort of collapsed down and started stars, when those stars early on, the big blue whites went bang, they produced some additional materials like carbon, some heavier elements.
Can you flip back to the previous picture?
Sure.
Isn't this going along with that one mostly or not?
Well, do you see hypernovas on there? Do you
No.
see any quarks or gluons?
No.
Well, there you go.
Where does this one start at?
This diagram was good in its day, but much like we once thought that the sun burned wood or coal, as you learn new things, and we're learning new things about when stars go boom and what's left over and how they cycle, this diagram is no longer, as they say, accurate. There is
Right, it's
more.
not accurate, but doesn't it have some
Yes.
something to write on it, right? Where did it start at, though? I forgot where she started. Helen usually presented this one.
The top center where it says sun-like star, it just kind of assumed that you started there because we have the sun. But where it actually started out is in the center where it says star-forming nebula. So prior to the existence of our sun-like star, there was a star-forming nebula. But where did the nebula come from? The nebula came as a result of a previous star going nova and blowing its guts out and producing the nebular cloud. Well, where did that star come from? Well, it came from a previous star-forming nebula that was from an early on. Our sun, I think the current statement is it's a 5th generation star, as in initially quarks and gluons produced the hydrogen that, star occurred, blew its guts out, another star occurred, blew its guts out 3 times, 4 times, and then you got the sun. So, our sun is around 4 billion years old, but the universe is several times that.
Now, this glucon thing I haven't heard of before.
Gluons?
Gluons.
Okay. So if you were to look at an atom, it has protons and electrons and neutrons. But what are those made up of? And if you remember the physics model of particles, and it showed, well, what's contained in a proton and what's contained in an electron. The things that make up protons and electrons are called quarks.
Yes.
And there's these funny named things of, up, down, charmed,
I like
strained. If you remember those, well, what was holding the quarks together were these things called gluons. Now, why did they call them gluons? Well, they were kind of like glue. They were holding the quarks together because the quarks, if left unto their own devices, don't like hanging around together. So what did you have holding the quarks together that made up the proton? Gluons. Okay.
Okay, so these gluons come together.
Yeah.
And
The gluons are holding the quarks together to make things like protons and electrons.
But you're saying the gluons are what come first before you have.
No. I'm saying we don't know what occurs before the quarks and the gluons, but we're supposing that as we break things apart further, we find stuff like the Higgs boson. So if we went back further, maybe we'd find that the Higgs boson is the precursor to quarks and gluons. So as we create bigger and bigger physics machines to break things into smaller and smaller components, we find more components. At one time, we didn't know what materials were made up of. And then we came up with molecules. And then we said molecules are made from atoms. But what are atoms made up of? Well, they're made up of protons, neutrons, and electrons. But what are they made up of? And as we smashed particles together harder and faster, and they would break apart into smaller, shorter lived particles, would go, oh, look, some stuff came out of that. And it either went straight out, or it took kind of a curl, or it took kind of a circular, and that meant they had different levels of energy. So the thing that goes on a curl is that level of energy, and therefore we'll classify that as this named subatomic component. So there's an entire chart of these things, and they give every one of them a name and a mass and a charge and a spin. So they can categorize all these things and give every one of them a name.
Okay, so now I want to go forward though. I don't want to go back. I don't want to get any smaller.
Okay.
I mean, I haven't been wanting to get any smaller since I came to the electrons. I thought that was small enough. They kept saying the atom's the smallest thing we have in, and then
you mean leptons.
So it was the smallest, and now nothing's ever going to be the smallest. But anyway,
well, so far the Higgs boson is the smallest.
Smallest, okay.
Yeah.
So now you have this matter that you had. I'm trying to find out what I really want to know is you got this, I can't say that word again, the stuff that's the sticky stuff. What's it called?
Gluons, yeah.
Gluons. You think of it as it's an adhesive glue, and then what is it doing? It's gluing onto
yes.
So gluons.
Remember, I don't know why I forgot it, but it's gluon.
Yeah.
So you have gluon, and it's getting all together, and it's going to start making this eventual sun-like star, right? That's
well, what happens is the gluons and quarks make up protons and electrons, and those make up atoms, and atoms of hydrogen, helium, carbon, dust. Those are brought together initially by static electricity, and then when they clump up a bit, they're brought together in a cascading effect by gravity, which we don't know what the carrier is for gravity yet. So there may be other kinds of particles out there. But as gravity pulls all this stuff together, it pulls it together so tightly that it fuses. And when it fuses, it produces lots of energy, and that's how you get a star.
But that happens like 5 times, you said, for our sun to be the way it is.
Yes, you go from the raw materials, the stellar forming nebula, to static electricity and gravity, collapsing that down, fusion turning on, star, and the star burns through its
But is
fuel.
it called a star at that point, or is it a sun? I mean, like the first time that it
The
is
sun is a star, nothing more special than that. It's just one of a kind of star.
one of a kind star.
No, not one of a kind. There are several different kinds of stars. They're all based upon how hot they are and how big they are. Our sun, Sol, is a very garden variety star. And, you know, it's what is known as a yellow dwarf star. It's actually greenish in color, but from ground level on Earth, it kind of looks yellow because of our atmosphere. So we call it a yellow star. It's a mediocre star. It's, you know, as the saying goes, nothing to write home about. It's just one of a lot of different kinds of stars. And there are more stars that are orange and red than there are stars that are yellow. And all of these yellow, orange, and red stars are all small. They're all dwarf stars. But
Okay.
you have bigger stars that are hotter, that are blue or blue-white stars. They can get to be fairly large. But that's just the star itself getting large. Now, once a red dwarf star gets out towards the end of its life, it swells up and becomes a red supergiant.
Okay. My question really has to do with I'm trying to make sense of this simple thing that I learned. I
Yes.
learned this and I want to still remember some of this stuff into the new process. If in fact it's applicable. I mean, do I need to erase everything that's on the
No,
script? Or
no.
what is it that I need to change? I mean, is this
What you
like
need to what you need to change is in the lower right hand corner where it just says supernova, done
uh-huh.
deal, supernova. There's now 9 different kinds of novas.
Okay, I can take
Only one of them is a classification of supernova, and within that there are 5 different subclassifications. So you have to break out that supernova into a lot more different kinds of things that can happen.
So you wouldn't call that a supernova now? You just call that an explosion time? Because I see
No, they're all explosions,
right.
but there are novas and there are supernovas and there are hypernovas, and then there are magnetorotational hypernovas.
And that's what I was saying. The biggest change on this grid
Yeah.
is that part there, except you did point out to one thing and that I didn't know was this gluon. And that gluon comes in at the sun-like stars. That's where
No. The gluons come in for how did you get your original star-forming nebula? You needed something to give you a lot of hydrogen. So
and we thought that was coming from the sun-like star before.
No, we picked the sun-like star just because that's what we've got right now. You are here.
Mm-hmm.
That's not where it started. That's just where you are now. So the other thing you have to change in the lower right-hand corner is you see it says neutron star and black hole. Well, there are now other things that can happen besides a neutron star and a black hole. You can have it cycling back to a star-forming nebula. You can see there's an arrow that does that. It goes from supernova straight back to star-forming nebula. So that's okay. But what about the one where you get a star out of it? It goes from supernova to a star. It's not a neutron star. It's not a black hole. And it's not a star-forming nebula. It's a star. So your star goes bang, you get an explosion. And then after the explosion dies out, there's still a star there. So the star doesn't go away. It doesn't shrink into a white dwarf. It's still a star. The other thing is, it says neutron star there, but there's several types of neutron stars. Depending upon how small and how tightly compressed they are, they could be a magnetar. So the basic concepts here are the same. It's the splitting out into finer designations that is missing from this. So it's not like you scrape this off and start from new. It's we found new things that are as a result of these, and that's the part that's missing. We found new science.
So, okay. So both sides are right then. It's just that
Well,
they
this is on the left. This is right for how our sun, in its instance, came into existence and what's going to happen to it. So the left side, that's a good example of where the sun started and where it's going to end up. But what happened before the star forming region? They need to add that. Well,
Okay.
what happened to the first time that happened? They need to add that. But the rest of it's okay. And on
Yeah.
the right side,
Okay.
if you
That's
on
what I
the
was
right
thinking
side,
too.
if you have a blue-white star that's bigger and hotter than our sun, what happens to it? Well, there you go.
Mm.
But when you get down to the bottom, there's several types of novas and there's several types of end products that aren't
Okay.
listed here.
Yeah.
So,
I was thinking that that's what happened, but I wasn't sure. But okay, thank you.
well, think
I
of
got
it this,
more stuff from it than
Yeah.
I thought.
think of it this way. When we had Newtonian explanations for gravity, when Einstein came along and said, no, space is curved, that's what gravity is all about. It didn't negate what Newton did. It explained what Newton did. It came up with more detail and offered finer detail. So that's all that we're saying
That's
now.
it.
Now that we've got the instruments and we're spending the effort to study what happens when stars go boom to a greater detail, we saw it was this beforehand. It went through this came out as a result, and then this was the residue, the end product. And look, it's back to where we started again. So we're finding that the process has different end results, not just the ones we thought of, and they can cycle. So, but they went looking down the periodic table of elements and said, where do all these elements come from? And somebody just said, they're formed in stars. We are stardust. We are the ash of stellar evolution. And somebody said, I don't think the math works. You can't just have them all forming inside of a star because the star is not energetic enough to fuse the heavier elements. How do you get the bigger force? Okay, when the star goes boom, the shock wave of the star forms some elements. And then they said, good, you've got these elements, but what about the rest of them? So that's why you come up with the P, R, and S processes for where did these elements come from? Well, they came out of the star when it was fusing. Well, where did these elements come from? They're heavier elements. Well, they came out of the star when it blew its guts out and the shock wave compressed. And okay, but that's still not enough. Where did the rest of them come from? Well, either when the star went boom, the outer shell of the star couldn't get out of the way fast enough, and that's where you have high energy. I said, but there's a couple that are left that you're not quite there yet. So to correct their simulations, they said, well, what if we just take two neutron stars and slam them together? That's about as much energy as we can crank out. It's enough to produce gravitational waves, which we know are exotic forms of compression. Okay, now you've got enough. Now you've got enough energy for it.
But why do you necessarily have to have enough energy to produce Einsteinium? Maybe there is no Einsteinium until we made it.
No. When we break things apart, we find these elements. So when we run through the colliders and we start finding these very short-lived things coming off of the explosion of that proton, we see that each of them, because they go a certain distance before they disappear, or because they curlicue at a certain arc, or they curve at a certain arc, it describes them. And that tells us what kind of elements they might form. And therefore we can fill in the periodic table based upon the energy levels.
Right. But what I'm saying is that if we found Einsteinium lying around the universe, then we'd be obligated to say, well, where could it come from? It had to come from an energetic explosion. The only energetic thing that's that energetic is the collision of two neutron stars.
Yes.
But since we don't find Einsteinium crystals with the dilithium crystals around the neighborhood, then maybe there wasn't something that energetic, and we just produced the Einsteinium when we produced those high energy collisions.
And I'll give you a homework assignment. The homework assignment is go
that's
back
no
and
good.
look in the last 2 weeks. There was a news article that they actually, through spectroscopic analysis, found uranium as the residue of a stellar explosion. But where'd all the uranium come from that's on the inside of the Earth? Well, that was fused in stars. In stars or from stellar explosions? Oh, now that we've actually found a star where we can see the uranium, it must have come from the stellar explosion. Well, was that the shock wave of the explosion that produced the uranium, or was that already inside the star and it's just the star blowing its guts out? So then they had to look at how much uranium is it as a percentage. And in the stellar cloud that resulted from the explosion, where is it? Is it in the outer edges as kind of a spherical shape? Is it dispersed throughout it? So that's your homework assignment is, they recently discovered that there was a stellar explosion where there was an abundance of uranium in it. And
yeah, but uranium is in our neighborhood.
Yes, it's inside the Earth. But where did we get it from?
From the stars.
But was it inside the stars? Or was it created when a star exploded?
That's from the shock wave.
Probably when it exploded, but that doesn't mean necessarily that there was anything greater than. No, I think now they actually have discovered natural plutonium as well, right? Isn't that
Well, plutonium is an oddball. It's an oddball.
Right?
Plutonium is in such short supply that it's almost a degeneration of more radioactive materials. And Helen does an excellent job of explaining where the plutonium comes from that I'm not going to even attempt.
Well, but that could be the answer. But if it comes from heavier materials, then that could imply there is Einsteinium produced, and then that means that we would have to understand that there was something higher energy, like the collision of two neutron stars.
Well, if you look at the periodic table of elements and you look up the radioactive metallic elements, you'll find that some of them are extremely short-lived, as in they decay into other more stable elements that might still be radioactive. And so that's why we don't find them in large supply, because they quickly decay. But when we blow apart protons, we can find those energy levels in particles that are as a result of the collision. So we do find and fill in the table with those short-lived, highly radioactive materials like Einsteinium.
Well, Monroe, you know that if you add the mass of the gluons in a proton, that it's much less than the mass of a proton, so you really can't trust them anyway.
Well, you can never trust an atom. They make up everything. What? No laughter? What an audience!
That was a good one. Laughing, you.
But I'm laughing.
You can actually buy a T-shirt on a number of websites that say, it's physics geeky T-shirts. You can't trust atoms; they make up everything.
They make up everything. Yeah.
Yes.
Yeah.
Now I get it.
Yeah. So the other one is, are you a proton Yes, I'm positive.
Yeah.
So there's a bunch of physics jokes that are out there. Not so many quantum physics jokes, but I think there may be some soon. If
Well,
I'm
that
going
may
to,
be the future of the thinking, is that there may be really no substantive matter. It's all waves and probabilities and
yes,
things like that.
if you
Yeah,
watch,
it's all fields. Yeah,
yes,
that's exactly right. It's all
if
quantum fields. You
if
got it.
if you watch that TV commercial for insurance where the guy is trying to teach people not to be their mothers and fathers when they buy a home, and how you can't have a plaque with platitudes on it hanging on your wall. That doesn't apply to me. I have lots of things that I printed out on letter size paper, and I've got them hanging on my wall. And one of them is about the difference between something that's invisible and non-existent. So whenever somebody says, well, it's dark matter and dark energy because we can't detect them. Well, so long as they remain non-detectable, they're essentially invisible. And if they're invisible, do you really understand all the subatomic physics? Or is it just that, you're just making something up to fill in the gaps? And, if you talk to physicists, they will tell you, we're calling them dark, not because we can't see them, but because we are using them to fill in the gaps in simulations.
There's nothing wrong with that. They were filling in
No,
the
that's
gaps.
fine. That's fine.
Yeah.
But I would rather them call them gap filler.
Yeah.
If you're ever into carpentry and you have scratches or holes in wood that you want to fill up, you buy plastic wood. It's a product and a brand, and it's a material that is a gap filler. Or if you're doing that with plasterboard, you buy a material called spackling compound, and you use that to fill in the gaps, smooth it off, sand it off, and paint over it, and you never know it's there. Well, I think that dark matter and dark energy ought to be referred to as the spackling compounds of astrophysics, because they fill in the gaps.
Right.
To refer to them as dark, it almost gives them some level of prestige they don't deserve. It just shows our ignorance.
Yeah.
But, as long as they get their research money to go look for it. I do like the one where, give us another $10 million because we haven't found it yet. That means it must exist.
Uh-huh. All right.
Fine. It gives people jobs. We create, instruments that are large, which takes lots of workers to build it and monitor it. And so it's giving jobs. I'm fine with that.
Yeah.
Okay, so in conclusion, there are many types or colors or temperatures of stars, and they can be all kinds of sizes: dwarf, main sequence, giant, supergiant. There's all kinds of stellar explosions. Some just aren't involving one star, they're involving multiple stars. The scales of the explosions are all over the map, and the size of the explosion and the energy in it is based upon why it happened. What is the factor and what limits been crossed? We can detect these in numerous ways, the two predominantly being photoelectric, as in it creates photons. The photons have energy. We direct those into detection instruments, which produce electrons. Those things we know measure everything. Electrons. And if it's not electrons, then it's gravitational fields. And we detect the gravitational fields by, crossing distortion fields that produce light patterns, which we detect as photoelectric electrons. So it all gets back to the electrons. When these explosions happen, many types of results are possible. You can have simply nebular clouds. It sort of all blows it into nothing. You can have a shrunken down white dwarf. It can collapse further into a neutron star or a magnetar. and then it goes exotic and collapses down into a black hole. So except for hydrogen, all the elements that we know about were produced in either inside of stars or through stellar explosions occurring over and over again. So think about that for a moment. Hydrogen has protons and electrons, and only certain isotopes have neutrons, but think of it as hydrogen as these two subatomic particles that are made up of quarks and gluons. So initially, if the Big Bang produced nothing but quarks and gluons, you'd get your hydrogen. And if you got your hydrogen, you can get everything else that we know in the universe. So if it was easy to classify all these explosions, and if we thought that science already had a good bead on this, we wouldn't be seeing these new observations and we wouldn't be having this conversation. So the more observations we make, the better we can resolve and categorize or classify stellar explosions. And that's it. Any questions? Comments? Did you get some new stuff out of this one that the previous sessions where Helen explained the life of stars?
Oh, yes. Oh,
Because
yes.
there's
Very much so.
there's new stuff coming out. So
It's amazing. It's getting smaller and smaller and bigger. Both, it works in both
Yes.
directions.
yes, the universe is getting bigger and the things we're finding are getting smaller.
Right.
So
We just have to continue of what we learned in school, but a little more.
yes,
I
yeah.
think there's some news, there's thinking that the universe has the shape of a donut. Yeah, this was true. True news.
But how can it be a donut? Everybody knows the universe is flat. Ask any astrophysicist and
I
they'll
don't
tell you
know.
the universe
It's a
is flat.
jelly-filled donut. I don't know.
Except those flat earthers, they're not right. When an astrophysicist describes the nature of something, he has to have something in his mind that is analogous to it based upon the data that they're looking at. So
Yeah.
when an astrophysicist describes the universe as flat, they're not describing it as flat, they're describing it as uniform. It's consistent. It's spread out evenly. It's flat, but it's not physically flat. Now, is it spherical? If it's spherical, is it a hollow sphere? If it's a hollow sphere, then that means all that exists is on the outside of this ever expanding sphere. Or is it like a torus? Is it like a donut shape? If it's a donut shape, that must mean there's a field holding the donut in its shape.
Yeah.
So where's the field coming from? Don't ask such questions because then the donut falls apart. So
Hey, they had a interesting bit on a show called Henry Ford's Innovation Nation. It's
Yeah.
on Saturday mornings.
Yeah.
So they had really good explanation of black holes and talk. It was very brief, but it talked about how they've discovered a new black hole,
yes,
and that was really cool. So if you can go back and ask for it on Xfinity,
mhm.
just watch the first part of that show.
There is a very well-funded research lab up in the Northeast. And I didn't know it existed until I saw, because I'm on academia and I get these articles that somehow manage to reference my name. So I go look at the article. And sure enough, somebody in the comments made a reference to something I spouted about, years ago. But hey, this guy said this. Is there any merit in that? And somebody will say, no, what does he know? Or they'll say something like, yeah, he's kind of right. Or they'll say something like, well, let me give you more information on that. And they'll quote something, but my name's stuck in the comment. So, you know, I found this research document that somebody said something about me, and I went and looked it up and I went, that's amazing. I never knew that existed. But they're building high energy, very low temperature detectors. And what they're doing is CERN, you know, gets their billions of dollars to build their giant donut shaped particle colliders.
Uh-huh.
In the US, we have a population that will not spend that kind of money, no matter how many people get a job out of it or what new science occurs. There's just not the interest to spend that level of money. But, you know, if we spend $40 million and we spread it out over 3 to 5 years, it kind of gets the noise in the budget. And that's where the Ford Institute has a research facility where they're literally building new instruments from scratch over several years' time. And it's so quiet, it's down into the weeds of the budget and does not get a lot of PR. But you need to go take a look for that. And I think you'll find it fascinating, because if you think that the Fermi Institute is the only place where the US is spending money on subatomic particle research, it's not. There's this other facility up in the Northeast, and it's not the one out on Long Island where they got the magnet from to, you know, haul over to the Fermi Institute and come up with, you know, this, I think it's called C2 muon postulation. I had to. Physics Girl, if you've ever watched her on YouTube, she's very educational and very interesting to watch. There's a YouTube page called Physics Girl, and she has a YouTube video on this discovery of muon C2 and how it's going to change physics forever. And it's based upon this. They detected something at Brookhaven on Long Island, but they didn't have the money to continue the research. But Fermilab did. They had a little change left in the wallet. So they spent the money to have the magnet removed from Brookhaven, shipped around the United States by ship down the East Coast, around Florida, up the Mississippi River, up to Chicago, to transport it by truck to Brookhaven and install it underground at Brookhaven so they could repeat the experiment. And they confirmed the experiment, and therefore it's physics. I said, wait a minute, when you move the magnet, was there anything you changed? No, it's the same magnet. Yeah, but you installed it at a different elevation above the core of the Earth. What's that got to do with it? So I sent them the article on how NIST, the National Institute of Science, Standards and Technology, found that their atomic clocks in Boulder, Colorado, differed than their atomic clocks in Gaithersburg, Maryland, by the last digit, out to like 8 precision digits of accuracy. And they found out it was because the clocks were at different heights above the core of the Earth.
Uh-huh.
And they went back and they did the research on it, and they found that you could put them at about a 1 foot distance separation. And now that they have even higher accuracy clocks, you can get the last digit to change in 1 foot difference between 2 clocks in the same rack.
Wow.
And so what NIST did out at Boulder and in Gaithersburg is not only have 3 clocks in 3 different shelves on the same rack, they actually have 3 different racks of clocks at different physical places in the time observatory, because not only is the distance from the core of the Earth a factor, the material between where you're at and the core of the Earth also has a differentiating factor in the gravitational field.
Yep.
Are you above something that has more water than stone? Or are you above solid granite? Gravity is different. Well, not so you could detect it, but when you get out to, eight fractional decimal places of precision, yeah, the last digit changes. So I sent this off to Fermilab, Brookhaven, and to Physics Girl. I'll just see what they have to say. Because the underlying bedrock and the elevation above the core of the Earth is different in where they installed the magnet between Brookhaven and Fermilab.
Well, sure. When did you send it off?
A month ago, I sent it to Brookhaven and Fermi. And just this week, I sent it off to Physics Girl just as a
Oh,
comment.
well, so it will take a while to hear.
Well, I'm sure they're going to go, who's this guy? What the hell does he know from anything? We're physicists. We're trained. We've got letters after our names. Like, okay.
Yes, sure.
But that's why I included the link so that, maybe you can talk to your brethren, because the National Science Foundation funds this stuff. And if you sort of go up the financial food chain, you'll find that NIST gets funding from NSF and Department of Commerce, and Fermilab and Brookhaven also gets funding from National Science Foundation. So there's some place where the funding comes together, and maybe they could talk to each other, because if you're expecting, Fermilab to talk to Boulder, Colorado NIST, that's just not going to happen, even if they're both well-respected physicists, because what has time got to do with muons?
Yeah.
Obviously something.
Oh, that's I love it. That's interesting.
Yeah.
Love it.
When I was out at the supercomputing center in San Diego, I looked at a number of the projects they were working on and found out that even if there were two projects, both funded by the US government, by your tax dollars, if they were in different divisions of the same organization, they didn't talk to each other, because scientific method says you don't want your observations to be tainted by other observations. So you almost create this procedural, logistical firewall between the efforts. So not only are they not talking to each other, they're deliberately not talking to each other.
Sure, they're enemies.
Until you get some jerk off the street like myself going, but what about this versus that? Now,
I love it. It's going to be interesting.
if they really are following the scientific method, it doesn't matter where your observations come from. If your observations are reproducible, you should take that into account as part of the evidentiary evidence, either for or against your postulation. That's scientific method. So we shall see. But a couple of months out, we'll have this presentation on the Spitzer Space Telescope, or the Webb, as they call it, and not the Spitzer, but the Webb telescope. And remember, the Webb is infrared only. It's near infrared and mid infrared, not deep infrared, because that's too close to radio. You need much bigger mirror than that. You might even need an antenna. But it's infrared only. But every one of the instruments on board the Webb has a spectrometer. And some of them have two kinds of spectrometers. They have slitless spectrometers, which are just a fancy way of saying camera. And then they have slit-based spectrometers, which is a fancy way of saying, we break the light into a spectrum. How are they doing this? What kinds of molecules can they detect if they're not looking all the way through the visible light spectrum? Because if you've ever looked at a full spectrum from infrared through visible to ultraviolet, you'll see that a lot of the elements do not have spectra, do not have lines, absorption or emission. just in infrared, but they do have some that are just invisible. I don't mean invisible, I mean just in the band known as visible to human beings. And one of them happens to be oxygen, which I found fascinating. So you mean we're sending up the Webb, and one of the molecules it will not be able to directly detect in the atmospheres of any exoplanets that they observe will be oxygen. Seems like a shortcoming to me. And then you find out they cannot detect oxygen, but there's another form of oxygen. Instead of being O2, it's O3. That's ozone. Ozone does have a spectral line in the mid-infrared range. So they cannot detect oxygen directly, but indirectly they can detect ozone, and the ozone typically comes from oxygen chemistry interacting, and you get this stuff that's broken apart by ultraviolet radiation called ozone. So, well, you got to look below the science, because if you just scratch the surface, they won't tell you their shortcomings. So if you ask the people that are working on the Webb, what kinds of molecules can you detect? All the precursors for life on a distant exoplanet.
Life itself.
Ask them, what about O2? Can you detect O2? Not directly. Oh, okay. Could you provide me a spectral chart for the mid-infrared to near-infrared bands of what molecules you're actually going to be able to detect? And I did the research and found out, yes, for every one of the instruments that are going to be on the Webb, there is a simulated spectral chart that shows what the possible molecules they can detect are with that instrument, operating with that filter in that mode. So obviously I had to make some of that stuff a part of my James Webb Space Telescope presentation. And yes, it will be in there. So I think when I run the content of the presentation by the folks at NASA, they're going to go, oh, this is too detailed. This is too heavily detailed for general population audiences. And I'm going to say, yes, it might be for the general public, but my audiences always like digging into these little trivial things that go, oh, that's why, or I didn't know that, or so that's why they can or can't do something.
Mm-hmm.
You know,
Sure. Yeah.
a couple of years ago, somebody said, we've done an entire infrared spectroscopic survey of everything around our solar system. How is it we didn't find the 9th planet? And somebody said, well, we know it can't be there because we've done this infrared spectroscopic analysis of the entire sky and we didn't see it. And I thought, infrared? Horse pucky. Think about the focus on a camera. If you take a camera with a 35 millimeter focal length lens and you zoom it in close, you can see the links in a chain link fence that's 6 feet away. The moment that you zoom the lens out, because you want to see things 100 feet away, the chain link fence magically disappears.
Mm-hmm.
The infrared telescopes that they've used to examine the entire universe to find where all the red and orange dwarf stars are in our galaxy, none were focused on finding things so close they could be considered to be in our solar system.
What a pity. They might have seen a few interesting things.
However, there is a telescope called the Hubble Space Telescope that can see an infrared. The problem is,
It doesn't.
no, it's working. It's back to operational. The problem is it's only looking for big stuff. like Jupiter, Saturn, Uranus, Neptune. It's not looking for stuff that might be in the Kuiper belt that's Earth size, or maybe even at that distance, Neptune size. It can't see it. It's too few pixels. So if you want to find the 9th planet and it's somewhere out in the Kuiper belt and it's not bright, otherwise we might have found it by now. It's dark, so it may be like, you know, a brown dwarf category thing, a failed Jupiter kind of thing. You're going to have something that has enough pixels to pick it up, and the focus has got to be on that depth of view.
Does the James Webb have that?
No,
No.
no. James Webb is looking way off in the distance because it's looking for exoplanets around other stars. It's not looking that close. Something in the Kuiper belt would be too close.
Yeah, obviously.
Yeah.
Mm.
And the other thing I found out about the Webb is there was a previous infrared telescope called the Spitzer Space Telescope. That's why I got confused early on and said Spitzer. The Spitzer Space Telescope, we don't use that anymore. And the reason is, if you want to find something that is almost at absolute zero, because it's hot, but it's so far away hot that it actually looks cold, you need to cool your detector down to almost 0 Kelvin, so you can detect that minute amount of heat energy. Well, to do that, your spacecraft needs a tank of liquid helium.
Yeah.
But you don't have that liquid helium for just one thing. Whenever you're flying around up there and you need to do any orbital corrections, you burn a liquid fuel called hydrazine. But if your tank is no longer full, the hydrazine will slosh around in it and will not make a good pressure to the engine nozzles. So what you do is you bleed off a little bit of your helium into the much warmer, not refrigerated hydrazine tank, which pressurizes the hydrazine liquid, so it puts pressure against the engine propulsion systems to make thrust. So even if you think you're going to be using your helium to keep your instrument cold, if you don't have a separate supply of helium for your hydrazine tank, you may find you're going to use up all your you're going to use up all of your helium pressurizing your hydrazine to make it squirt things to keep you on course rather than keeping your instrument cool. So when you have an instrument like a Spitzer Space Telescope, it has enough helium on board for about 5 years of cold observing. Once it runs low on that, in order to keep itself oriented properly, it stops cooling the instrument. It goes into what is known as a warm or hot period, where the instrument is running at the temperature of open space, which is not that hot. It's still pretty cold. You know, it's below freezing, but not cold enough to detect the darkest, dimmest things, because you need that helium to keep your hydrazine pressurized until you run out of hydrazine. And when you run out of hydrazine, you just start to drift. And if you drift into a place where we don't want you, that's bad. So you can't completely run out of your hydrazine. As you get really low on hydrazine, you use the remaining hydrazine to push you into a different place so that you're not occupying a valuable spot for something else. So if, for example, Spitzer was in one of the Lagrange points, let's say L2, which it wasn't, I think it was in L1. If it was in L2, as it got low on hydrazine fuel, after it was already in its warm state, you had to use the remaining hydrazine to get it the hell out of there, because the Webb telescope wants to be in L2. It can't just sit there. It's got to get the hell out of there. So it uses its remaining hydrogen to exit the expensive real estate for the cheaper places. And so Spitzer wound up being in this Earth lagging orbit. So once you leave the stable L point, you're no longer going to be orbiting the sun as fast as the Earth. You're going to start slowing down. And as you slow down, eventually the instrument will have the sun in the way. So think of the Earth going around the sun, and the Spitzer is slowing down. So the Earth is kind of going out ahead of it. And as the Earth goes around out in front of it, now all of a sudden to get a radio signal to the Spitzer, you're having to point too close to this giant radio interference thing called the sun. So you got to give up on Spitzer. So that's what happened to the Spitzer Space Telescope is it lagged back after it was out of its L point. And eventually you just got, it didn't get like close enough to the sun to burn up. It just got too close an angle to the sun for us to reliably communicate via radio communications with it. The sun got in the way. That's the ultimate fate of the Webb after about 10 or so years. So the Webb will have about 5 years worth of helium to keep the instrument cold. And then it'll go through about 5 years of warm or hot. And then as it gets to the end of that, you better leave that L2 because we got another telescope coming out there. They've already got that one planned. It's going to be another infrared telescope. It's going to be getting a new name. You know, it's going to be commemorative, named after someone. But I think it's currently called FAST. I don't know how they get that, but oh, not FAST, FIRST. It's called FIRST. I needed to find where the I for infrared came in. So it's called FIRST or W FIRST. It'll eventually get its commemorative name. But that is the telescope they're already designing and working on. There will be the follow-on to the Webb, and the Webb is the follow-on to the Spitzer. So Webb is not really the follow-on to Hubble because it only sees in infrared. But it is the follow-on to Hubble because much like the Hubble sees in infrared, the Webb will see in infrared only better because it won't have the sun and the Earth occasionally blinding it, and it will be beyond Earth orbit, so it won't have to put up with the Earth getting in the way. But the Earth will still get in the way because the orbit that the Webb will have is out beyond the moon at the L2 point. Now, if you ever look at the L2 point, L2 itself is stable, but the Earth and the moon are in the way. So how do you get out to L2 where it's almost stable, but you can create an elliptical orbit that takes you out far enough away that you're not looking back towards the Earth and the sun? It's called a halo orbit. Part of the halo orbit, part of the ellipse of the halo orbit is using light pressure from the sun to kind of push it around. The other half of the halo orbit is hydrazine firings. So that's how it uses up the hydrazine.
Interesting. I didn't know that. I didn't read on that.
These are things I'm learning about the Webb that will be included in the presentation, that if I go look at one of NASA's, Webb telescope presentations they have out there now, they don't dig that deep, but we'll dig that deep. How else am I going to fill up an hour and a half to 2 hours worth of me blathering?
Great.
So
Super.
okay, any other comments or questions?
Thank you very much. Very nice.